All right. Hi, I'm Gaurav. I'm a second-year PhD student at Carnegie Mellon University, and I'll be talking about a new approach to this problem of gradient estimation, which is essentially about differentiating probabilistic programs. So in standard automatic differentiation, we take a user-written program which implements a mathematical function, for example, theta squared plus 1, and produce a new program which computes its derivative, for example, 2 times theta. And modern tools for automatic differentiation, which are very widely used, have taken this basic idea and extended it to programs featuring loops, mutation, arrays, and so forth. And the basic idea here is to take an input program t, which denotes some mathematical function, and synthesize a new program t prime, which denotes its gradient. But what happens if our input program features probabilistic constructs? So on the left here, I have a probabilistic program which samples from distributions, such as a Bernoulli distribution and a Gaussian distribution. In this setting, every time I sample from my program, I may get a different value drawn from some underlying probability distribution. So how can we usefully generalize automatic differentiation to this setting? Well, an observation we can make here is that although each individual sample here may not be differentiable, the expectation of these samples may very well be. So for example, for this program here, we can actually write out its expectation symbolically as a function of theta. And this is a perfectly reasonable function to differentiate with respect to theta. But there's a catch here, which is that for a general probabilistic program, it is completely unreasonable to hope to be able to calculate its expectation in closed form efficiently. And so it is similarly unreasonable to hope to be able to compute its gradient exactly. So we have to relax our goals slightly. And instead, let's ask for a new program t prime which unbiasedly estimates the gradient of this expectation. So this new gradient estimator program will be a new program which we can sample from, just like the original program, but with the key property that the expectation of samples drawn from this new program t prime is equal to the gradient of the expectation of samples drawn from the original program. So gradient estimation is very broadly applicable. It's useful whenever you want to optimize or compute sensitivities of a probabilistic model with respect to its parameters. And indeed, over the decades, gradient estimation has found use in a wide range of fields, including queuing theory, biochemistry, neural networks, and so forth. So in the work I'm presenting today, we present a new approach to this problem of gradient estimation called gradient inference. And gradient inference has two main goals. The first is to unify existing gradient estimators. So over the past few decades, a wide range of existing schemes have been developed, including pathwise estimators, score-based estimators, phantom estimators, and so forth. And gradient inference aims to provide a common mathematical framework in which we can express and connect these different schemes. The second, and probably most important goal of gradient inference, is to enable the design of new gradient estimators. So when dealing with unbiased estimators, the name of the game is lower variance. And as a practitioner, applying gradient estimators to challenging applications, often your bottleneck is the high variance of your estimators. So gradient inference aims to synthesize new gradient estimators that are lower variance than the state of the art. So how do we accomplish these two goals? The key idea is to convert a gradient estimation problem into a probabilistic inference problem. So probabilistic inference is in the title of the session and has been quite well studied in programming languages. And the key idea here is rather than treating gradient estimation as a wholly new problem to solve from scratch, we'd like to be able to leverage the rich existing infrastructure for probabilistic inference to improve the design of gradient estimators. And our approach is automated in a new programming system called GradInf. So for concreteness, let me give you an example. So in queuing theory, the flow of packets in a network queue is often modeled as a stochastic process in time, where packets either enter or leave the queue. And so by sampling many random trajectories from this process, we can estimate the expected number of packets in the queue after a certain number of events. And of course, this expectation will depend on our model parameters. So if we, for example, increase the arrival rate of packets, then the distribution and the expectation unsurprisingly shift upwards. And in this setting, a natural question to ask is what is the sensitivity of this expectation to the arrival rate of packets. And this is precisely a gradient estimation problem. So let's see how GradInf attacks this problem. The first step is to rewrite this queuing model as a probabilistic program. So this is a model that is parametric in the input parameter we want to differentiate with respect to, and from which we can sample different outputs. So now, rather than trying to synthesize an entire gradient estimator program in one fell swoop, what GradInf does is it synthesizes a so-called inference target program. So this is itself an ordinary probabilistic program, which means it can be targeted with well-understood methods for probabilistic inference, such as importance sampling, stratification, sequential Monte Carlo, and so forth. And so in gradient inference, we actually synthesize a gradient estimator program by applying standard libraries for probabilistic inference and automatic differentiation to this inference target. So a theme that may have been apparent in the previous slide is that gradient inference is fundamentally compositional. So the input to GradInf is a higher order functional probabilistic program. To synthesize the inference target you saw in the previous slide, GradInf applies program transformations for coupling and for factorization, which are two variance reduction techniques that are baked into the inference target. Finally, existing inference and AD methods are applied to form a sound gradient estimator. So before I dive into some of the key details here, I want to give you a preview of the payoff. So for the queuing model I defined, GradInf can both express existing state-of-the-art estimators, such as score-based estimators and phantom estimators. And moreover, by swapping out the probabilistic inference algorithm used in the phantom estimator for one based on exact variable elimination, GradInf can achieve a 100 times variance reduction. So now that I've given you a preview of the payoff, let's discuss some of the key ideas in gradient inference, starting with coupling. So coupling is an idea that's found use in programming language literature, mostly for proving properties of probabilistic programs. But let's see why it's also useful for gradient estimation. So on the left here, I have the target gradient of an expectation that we're interested in. And on the right, assuming for simplicity that we have a real valued parameter, I've written just like the Calculus 101 expression for this gradient as a limit. And what I want to draw your attention to is that the numerator here is a difference of an expectation evaluated at the original program and an expectation evaluated at the perturbed program with parameter theta plus epsilon. And the existence of this difference of expectations motivates the formation of a coupling. So the key idea behind a coupling is that if I have two random variables, one distributed according to the original program, xa, and another distributed according to the perturbed program, xb, then by linearity of expectation, the expectation of xb minus xa will always equal to this target difference irrespective of our choice of joint distribution. And so we can choose this joint distribution to minimize the variance of our difference estimator. And this choice of joint is precisely the notion of a coupling. So in GradInf, we apply a coupling program transformation to our input program t to produce a new program c of t from which we can sample pairs of values, with the property that if I sample a pair xa, xb from our program, then xa and xb are guaranteed to be marginally distributed as we desire. And so I'll direct you to the paper for the full details of this transformation, but I want to give you an example of how it works on a flip primitive. So in the flip primitive, we accept a probability and flip a weighted coin, returning true or false randomly. At the type level, the coupling of this primitive now accepts two probabilities and returns a coupled pair of booleans. And on the right here, I have one example of a sound coupling that fulfills this type. So this coupling accepts a common random number omega and thresholds it against both of the input probabilities to form a coupled pair of booleans. So once we've defined the coupling transformation on each probabilistic primitive in our language, it automatically synthesizes couplings of arbitrary input programs. So on the right here, I'm showing the coupling of the queuing model program from before. And so this is a program that operates on pairs of values. And for those familiar with the notion from relational proof logics, this program can be understood as a probabilistic product program. Let's move on to the next step in gradient inference, which is factorization. So recall that once we formed this coupled program, we're interested in the expectation of this difference estimator, xb minus xa. And a classic variance reduction technique we can apply here is to condition this estimator on some information f, which by the Tower property of expectations is guaranteed to preserve unbiasedness, but also gives a provable variance reduction. So we'd like to apply this variance reduction technique to form better gradient estimators, but there's a question, which is what information should we condition upon? And the key idea here is to set f to the random value sampled in the fragment of our coupled program, which computes only the first component of coupled pairs. So let's see how this affects our coupling primitives from before. On the left here, I'm showing the common random numbers coupling of a flip primitive. And on the right, I'm actually showing the exact same coupling denotationally, but written such that we first sample the first Boolean, and then sample the second Boolean conditionally upon the first Boolean. And so this is a factorization of the original coupling. But we'd like to be able to surface this factorization structure at the type level. And so we have a type system wherein those random choices which determine the first component of coupled pairs are annotated as primal, and the remaining choices are annotated as residual. And what's lurking underneath the surface here is a non-interference property, where residual random choices are prohibited from affecting primal random choices. And so this type system is based on generalizing the classic dependency call calculus of Martin Abadi with probabilistic constructs. So in gradient inference, the way we exploit this new factorization structure is by forming a partial evaluation of our original coupled program in the following sense. All of the primal random decisions, which determine the first component of coupled pairs, are made to be deterministic, based on a fixed random seed, while all the remaining residual choices are left untouched. And to summarize what we've done here with coupling and factorization, we've synthesized an inference target program whose expectation is precisely this coupled and conditioned difference estimator we wanted to form. So now the role of probabilistic inference will be to efficiently estimate this expectation. And to give you some motivation for why probabilistic inference may be useful here, observe that only those coupled traces where xa and xb differ actually contribute to this expectation. And so the role of probabilistic inference here is to sample those coupled traces where the event xa not equals xb holds. And one reason why probabilistic inference is especially useful here is recall that xa and xb are drawn from very similar programs. One was the original program with parameter theta, and the other was the program with parameter theta plus epsilon. So as epsilon goes to 0, the probability they differ actually, with many couplings, will go to 0 as well. And so probabilistic inference can give a substantial variance reduction here. The final step of gradient inference, after having baked in all of these variance reduction techniques into this difference estimator, is to convert this difference estimator into a gradient estimator by applying standard automatic differentiation methods. So I'll direct you to the paper for details on our soundness arguments, but I'll just remark that like the gradient inference pipeline itself, our soundness proofs are compositional, and to push our proofs through for higher order probabilistic programs, we make use of quasi-Borel spaces and proof-relevant logical relations. To conclude, I'll demonstrate some of the applications of gradient inference. We consider a few in the paper. So in mathematical finance, practitioners care a lot about measuring the sensitivity of the prices of options to model parameters. And in this setting, GradInf is able to synthesize gradient estimators with asymptotically lower variance with respect to simulation time. Another important application of gradient estimation is in biochemistry. So on the left here is a reaction network model, and these models are often used to model processes such as gene transcription in the cell. And in this setting, GradInf is able to facilitate significantly faster inference of optimal model parameters when used in stochastic gradient descent. We also studied the expressivity of gradient inference in the paper. So we showed that a number of existing gradient estimators can be expressed compositionally by combining different factorized couplings with different probabilistic inference algorithms. And to conclude, our contributions are a new mathematical framework for gradient estimation, which we call gradient inference, a system which automates gradient inference called GradInf, soundness proofs, and a demonstration of substantial variance reduction. And finally, if you're encountering challenging gradient estimation applications in your own research, I'd encourage you to reach out, because maybe gradient inference can be of use. Thank you very much.
All right, questions? I have perhaps a naive question. So if we write a probabilistic program, how do we know whether the gradient of the expectation of its output is well defined?
It's a good question. So in our soundness arguments to the first approximation would sort of be our approach is correct, assuming it exists. So we don't, that would be a property which you need proof logic, so there's also been a lot of work on like smoothness tracking, and like it is a tricky problem to verify that for sure. There's other works which do that.
So there do exist methods which focus on checking whether a gradient of the expected value exists.
So for example, I think Alex, your ADA paper would like provide like a certificate which would, as a corollary, verify that property. Is that fair to say?
Yeah, or give you a verification condition.
Yeah. Okay. Yeah.
Hi, great talk. I really enjoyed it. So back to one of the applications, I think the second application, were you learning some of these parameters like alpha, beta, and stuff?
Yeah, I wasn't clear about that. So this is a parameter inference application.
Parameter inference, yes.
We have a loss, so it's not a Bayesian setting, so it's a bit of a heuristic loss to define the parameters which best fit the data. And we're using our gradient estimators to determine the optimal parameters.
I see, so the gradients are used to search for those parameters. Okay, sounds good. Thanks so much.
Just a curiosity, since you mentioned it, how do you use the proof-relevant logical relation? Is it for the information flow part or no?
No, it's used even for the proof of the soundness of our coupling calculation. So let me go back to, so we want to show that for any input program, input term of any type, its coupling belongs to some coupling logical relation. And it turns out that, I think the inductive step for probabilistic bind, you want to be able to access the quasi-Borel space morphism, which pushes forward the coupling proofs. And that's sort of why you need to relevant logical relations.
Okay, thanks.
We have time for one more question. Yep.
Hi, really great, really good talk. My question is it possible to apply this algorithm in reasoning about parametric family, like the distribution's parameter is not certain? So it's possible to reason about this?
Yeah, definitely. Are you thinking of for example, maximum likelihood estimation?
Yes.
Yeah, definitely. Then if you're doing that in a gradient-based way, or you're doing something Bayesian and you want, well, Bayesian's a bit trickier because stochastic gradients are a bit tricky, but definitely for maximum likelihood estimation, it's immediate time use gradients. Also for variational inference.
I see.
So yeah, in all those settings, gradients.
Like the robustness of the probabilistic programming.
Sorry, can you say that again?
Like the robustness of the Bayesian programs.
Yeah, it could probably be used for robustness.
I see. Thank you.
Okay, let's thank Gaurav again.